Hi-oh, color. Turns out color is nothing more than an expression of one part of the electromagnetic spectrum. Your eyes pick up only specific parts of the spectrum. We call that the visible spectrum. As the frequency changes of a wave, so does its wavelength. Because remember, these are all traveling the same speed, right? The velocity of the wave is the frequency times the wavelength. So as one changes, so does the other. Well, our eyes pick this up, and all due to something called resonance. Those frequencies cause the cells in our eyes to resonate, which sends a signal to our brain. If you look at the different colors, and I want to point out this indigo in a moment, down here at the red end, we have really big wavelengths. You can see it over here. But because the wavelength is big, the frequency is small. As the frequency changes, we move all over here to the violet end. The frequency gets much greater, but the wavelength gets smaller. Now, on the EM spectrum, a way to remember this, there's red, and then there's before red, or infrared. There's violet, and then there's beyond violet, or ultraviolet. A word about that indigo does not really exist. The white light that you see is composed of all the different colors. And to say black is a color would be incorrect, because black is the absence of any of those colors. There is no color there. The interesting thing is our eyes only need to see 3 colors to make up all other colors. And we call these the primary colors. Red, green, blue. RGB. Red, green, blue. If you look at a television screen, take a magnifying glass and look at a monitor, the pixels that make up, pixel is a word for picture element, that make up the screen are composed of those 3 colors. As they blend, as they turn on and off and half turn on, you get the different colors. Something with a very good resolution to the screen, those pixels are smaller. There are secondary colors, and it's the blending of those. For example, red and blue make magenta. Blue and green make cyan, and green and red make yellow. So the secondary colors are a combination of 2 primary colors. Just as a side note, we're going to not focus so much on on ink color subtraction, but I wanted to point out that as you were to magnify, you would see there are 3 colors that are used for printing, and that's those secondary colors of light, the magenta, cyan, and yellow. And of course they use black to highlight. Just a side note, those are the primary colors of paints and pigments, not blue, red, and yellow, like your art teacher suggests. The ones that your art teacher tells you are called psychological primaries, but they're not really primaries. So, the term complementary refers to having 2 colors that make white light. The only possible way to have 2 colors make white light would be to have a primary color and a secondary color. Remember, up here's the primary, a secondary is composed of 2 other primaries, and there's only 3 primaries. So when you see a color, it's because that color is hitting your eyes, right? If you can't see something if it doesn't hit your eyes. So you see the color because it hits your eye. The pigments in a substance, the chemicals in a substance, either absorb or reflect specific frequencies. So if I see red, like the color of my pen here, it's because the screen, if this were not giving off its own light, would be reflecting the red and absorbing all other colors. Because right now I have a white light shining down on me. So those dyes inside a substance, those chemicals inside a substance, start resonating to all colors except for red. And because of that, it heats up the substance. If you look in the upper left-hand corner, these are the basic blocks of of, uh, of color with white light shining on them. But what happens if we change the light source? For example, originally our red block, we know, only reflects red. All other colors in that white light source is being absorbed. But what happens if we don't shine red on it? Right? If this is only reflecting red and there's no red to reflect, that means nothing reflects. So it would appear, of course, black. Here we have a light source that is a combination of blue and green, and we call that, if you remember from a previous slide, cyan. There's no red in there, and you can see our red block is no longer red. So color depends on what you see based on the light source. So our ultimate goal is to apply that, and I came up with a table to help you do that. We want to know what the color of the object appears. And the secret to this is, what color does the light source and the object have in common? Let's look at the white light. The primary colors in white light, of course, are red, blue, and green. What colors are absorbed by the tomato? Well, that would be blue and green. And red is reflected, right? It's a regular tomato under white light. So the color appears red. Magenta light. What is magenta? Magenta is a combination of red and blue, which means of those three colors, we only have red and blue. We're missing the green. So a red tomato, we know under white light conditions, reflects only red light, which means everything else is absorbed. Well, magenta light has red and blue, which means the blue is absorbed. So what color does it appear? Look at that. Our tomato actually appears red still. But let's go down. Let's go to this last one. Let's go to yellow light on a blue flower. Yellow light is a combination of red and green. A blue flower reflects blue, but there is no blue to reflect in here, is there? Which means red and green are absorbed, which means if there's nothing reflected, the flower will appear black.